all. So we are starting the second part of series, which is super, super cool. So we're going to talk about what's called Taylor polynomials and use those to approximate some functions that might be difficult, but we're going to make it so that they're not, and it's really so much fun. All right, so here are essential questions, so if you want to look over those, and here are the objectives that the AP Calculus BC has set for us. Okay, so we're going to start this conversation kind of thinking about what was a tangent line. So if you remember, like maybe we had some curve going on and we used this to get a tangent line. We said, well, the slope, like let's say that again here at some c value for x. So then we'd have this y minus f of c, and then the slope was that first derivative that we had to take, and then x minus c. And I could bring this over and maybe like this is where my c value was, and so I made my tangent line right here. Okay, so basically we were saying that when I went and solved for this, oops, sorry, that's a plus right here. When I went and solved and I got this tangent line, that's linear. So lines are linear. Imagine that. Okay, and so here at this point, if I zoomed in and zoomed in and zoomed in on that curve, and I kept zooming in, eventually it's going to match the tangent line. And so we're saying that we have matched a line with the curve at this value. So now what we're going to do is we're going to get a polynomial, because the line's a polynomial here, and we're going to try to match it maybe a little bit longer with a parabola or something like that, or maybe even longer, with a cubic. Or that was like more of a fifth, but anyway, quintic. So that's like going to be our objective of what these Taylor polynomials can do, is they can match our function for a longer period of time than just one point from the tangent line. So let's just review really quick of how we found a tangent line. So we would take the first derivative of this guy. Remember, rewrite to the power rule so that we can take that derivative. And we can plug in our value. So here, the x that we're centered around is that 8. And so let's see, that would be negative 4 over 3 times the cube root of 8 is 2, 2 to the 4th, 2 times 2 times 2 times 2. What am I? I'm plugging in the 8. 4/3, sorry, I just had a momentary lapse. Okay, so that would be 2, 2 to the 4th, so 16, and then reduce that, 4 to 12. So then I can go ahead and plug in to get the original. That would be 4 over 8 to the 1/3, 4 over 2, which is 2. And then I can use my y minus y1 equals my slope times x minus x1. And I can solve for y. So this is a line that we could have to approximate what is going to be going on here. So whatever that curve looked like, this, if I zoomed in and zoomed in at the when x is 8, wherever that would be, then this would look linear. So if you look, this part right here, that is what we just did up here. Okay, so in this pattern, all we're doing is extending it out. So what is the pattern? Well, it's basically like the first derivative, then the second, then the third, then the fourth, etc. So this one is saying no derivative. And then you take it times the function x minus c to, if that's the first derivative, to the first power. If that's the second derivative, to the second power. If that's the third derivative, to the third power, etc. And then this is the part that might be like, what? Okay, is that you divide by, again, if you're on the second derivative, then 2 factorial, the third derivative, 3 factorial. So the nth derivative in factorial. And over here, even on that first one, we were doing that because x minus c, if I haven't taken any derivatives, would be to the 0, which is just 1, and then over 0 factorial, which again is 1. So see, I can see that that's been reduced. This was over 1 factorial, which again is just 1. So it's been reduced here. So we didn't need it. And then we have this special one that if we're centered at 0, the Taylor polynomial just gets a special name called the Maclaurin. And I just think of like a Big Mac. And if you had to ever take a bite of a Big Mac, your mouth, to get it, makes this O shape. And that reminds me, oh, we're centered at 0 because we're trying to eat a Big Mac. But that's called the Maclaurin. So anytime you see that word Maclaurin, it is talking about where we are centered at 0. And if we're centered at 0, it kind of makes life a little bit easier because all of these C's are zeros, so we don't even have to see them. We don't have to see them. Okay? So kind of our steps in doing this is to take the derivatives as far as we need to go, plug in those C values into the derivatives to get the outputs, and then use the pattern, use the formula for as far as you need to go. And this, like if I said go to the second, then I would stop right there. If I said go to the third, then I would stop right there. So that's just a little sub notation to help let you know where you're going to. Okay, and this is what I kind of talked about of what we can do now is if we have this function and it's like this is the original function, okay? So we have like the sine function, and I am trying to match to get some kind of polynomial to match it for a while. And I can go on different degrees and keep going and going and going, and I might be able to match it longer and longer and longer, and maybe infinitely we can match it to a polynomial. So it's saying instead of just getting some kind of tangent line at a point, now we're going to match it for a lot longer. Okay? Hopefully for a lot longer. Actually, sometimes the curve, like a quadratic, still may only match it at that one value. And we're going to see those. Okay, so let's do an example. Find the Maclaurin Big Mac centered at 0 of degree n for this polynomial. So it wants me to go to the 5th degree. So I need to take this function and go all the way until the 5th derivative. They just kind of alternate signs here. So you're saying that that's like an alternating series? Oh my gosh, you're so smart. And you can either use Roman numerals, or if you put a 5 in there, you're just supposed to use parentheses so that you know that the 5th derivative or something like this is like the 5th power. So don't do it that way for derivatives if you use the 5. Otherwise, you can use Roman numerals. And then we're going to go plug in our 0 because that's where we're centered. And I can see that this goes 1, -1, 1, -1, 1, -1, all the way to the 5th. And then we're going to use our pattern of what that general p sub 5 of x would be. So in general, I know that I need to go out all the way into the 5th. And then that's where I'm stopping because it wanted me to go to get the fifth polynomial degree. So then I can plug in what we had. So here, f of c was 1, f prime of c was -1, and I'm centered at 0, so that's just x. And then I had a positive 1, centered at 0, so that's squared. And then I had a -1, a +1, and then I had a -1. And I don't have to have those ones there, but I just wanted us to kind of see. So now the really cool thing that I'd love for you to go see is to go put this into your y1 and then go in your y2 and put in that original function and look and see what happens around 0. So go look at that. Pause me and go see what happens as those two guys when you plug them in around 0. See if they match up, okay? And then unpause when you're ready. Okay, so I want you to go ahead and try this one, and I'm going to show you what you should get. So pause me and see if you can try this one on your own. And at the very end, I want to see if you can get to this. Okay, so once you unpause and you check to see if you get to what I have, you don't have to go reduce any of those like fractions together. You can leave it just as you see it. Okay. All right, so let's try this next one. I want to do this one together because so many people mess up. And if you look on the signs, so you're seeing like some negatives and positives and all kinds of fun stuff. And so I'd like to do this one together for us. So here's my function. That's a 3. So then I have to take my first derivative. So derivative of the inside over the inside. And this is my trick that I think is so much easier if you have to keep going on the derivatives, is to rewrite this so that you use the chain rule instead of trying to do a quotient rule. So I'm going to take the second derivative now, so I bring that negative down, and now that's a +1. So the -2, but I still have times the derivative of the inside, which would then turn it negative. So you can see you had basically 3 negatives going on. So my third derivative, I'm going to multiply here, which is now a 2. But I'm going to take it times the derivative of the inside, which is negative. So then it says I'm going to go put 2 in for all of those. So that would be the ln of 1, and hopefully you guys all know, oh, that's 0. So the first term is a 0 term. Then I'm going to go ahead and think of it like this when I plug in my 2. And my second derivative, squared. And my third derivative, so then I have these coefficients. Then where people start to mess up is one more time, right? So pay attention to the negatives, and then also don't forget to divide by the factorials. So we're going to have that third degree is what we're looking for. We have the first term, and then the coefficient of the first term, and then the coefficient of the second term. And now when this is squared, I know I have to divide by 2 factorial. And then the coefficient of the third term with still a 3 factorial. So now once I have that, I can simplify to get to the answer of B. Okay, next one. This one is kind of nice because they just gave you the derivative values. So it makes your life a little bit easier to just say, oh, as I go plug these in, I want to go, let's see, does it say the third degree? So I want to try to get to that third degree. And so we're approximating what g would be basically by getting to this polynomial. So I'm going to have my first term and then the second term times x minus, what do we plug in? So minus a negative is a positive, and then my second derivative squared, and then don't forget to divide by 2 factorial, and then the third part, and then that's where I'm going to stop because it wanted for the third degree. And then the question said, if I plugged in g of -2, what is that now approximately? So now I'm going to plug that in for all the x's that I had above and solve. So -2 plus 3 is a 1. Oops, that's a minus. Then we need to reduce this and put all those together, and I get A. A. Okay, why don't you guys go ahead and pause me and see if you can do this next AP Classroom. Just don't forget, derivatives of C go negative, okay? And see if you get to D. And then unpause when you're ready. Okay? So hopefully you got that last one okay. If not, we'll talk about it in class. And let's go through this one. Second degree Taylor polynomial about 0. So about 0 is on this line. Oops. That. So this is with the 0 part. So first I'm going to go ahead and get that second degree Taylor polynomial. And if I'm about 0, there's no minus, which is nice. So that's to the second degree. And then it wants me to approximate f of 0.2. And since this is a free response, I'm not trying to match it to anything, leave it. Don't go any further. That is great. You've got it all down to a numerical value. It's just all numbers and operations. So done. Drop the mic. Okay. Okay, B is giving me that G is f of x to the third. So if I'm looking at f of x to the third now, then basically I'm going to kind of have what I wanted before. So this is now, and plug in everywhere I see an x, I'm going to plug in an x to the third. Because this, remember, was the approximation of what f was. So if I want f to the third, then I'm doing a substitution to plug in the third to these values. So x to the third squared. And holy moly, look, this is already now to the fifth degree. And it wanted me to go to that fifth degree. So I've got it. And a lot of times they don't make you do an extra step, but sometimes they will, where you maybe had to go up and do like one more term here to get to the fifth. But in this case, we didn't have to. And then it wants me to do what with that? Take the derivative. So derivative of 4 is 0, and then I have 15x squared, and then minus 5x to the fourth over 2 factorial. And Oh, look, I had to get to the G prime. Oh gosh, you guys, I messed up. I'm so sorry. I can do math. Oh, power to a power. Were you guys all yelling at me? That's a 6. It wanted G prime to the 5th. Oh, caught myself. Sorry. Okay, so this is to the 6th. Thank heavens. Otherwise, because I got stuck and I realized, oh my gosh, I made a mistake. It wanted G prime to the 5th and I only got it to the 4th. So I did just make a little mistake. Sorry. Okay, so let's look at this. Um, this one right here, derivative was 0. That part was still okay because power to a power, multiply. Okay, so we got it to the 6. So now when I take this derivative, now I'm to the 5th. Yay. Okay, so it wanted the 5th for G prime. And up here, I had done the 5th for G, and that would have been wrong anyway because that was to the 6th. Okay, but now we're good. And if you want to simplify that, go for it. If not, you don't have to. That's a free response. This one, if you want just some extra practice, go ahead and try it. Okay, you should get out -3/8 if you reduce everything. But otherwise, if you want to try it together in class, we can, or it's really just some extra practice for you. This is one where I definitely think the chain rule as you keep going through should help you. Okay, so now our next really big thing that we really want to know. So we have learned the alternating series error bound. Now we're going to do this Lagrange. You can say that word. Your parents won't think you're strange. Just say Lagrange. Okay, so the Lagrange error bound is really, really similar to what we saw the setup for the alternating series. But now it's kind of saying that the original function minus that Taylor polynomial approximation to the nth degree, and then we have the remainder. Okay, so this right here, this is the actual function value. So whatever that x is that they're telling you. This right here is the approximate value from the Taylor polynomial. And this is basically your error. This is like when you subtract whatever you are plugging in for x, they're telling you. So we did this a lot with tangent lines. We'd say, okay, go find the tangent line, and then maybe we centered it at 2. And we said, over here, go approximate what 2.2 would have been on F with what you had on the tangent line. And so we have this error going on between the two when we approximate. We often talked about, oh, we're concave down, so that approximation was an overestimate. And so we did this with tangent lines. Now we're just going to do this with more of the polynomial itself, not just a tangent line. So this is the x value that you're going to use to approximate. It is not where you are centered. It's the x value that you're kind of plugging in for your approximation. So this is not your center. Your center is what you use to get the functions. So what is that error? Well, in the alternating series, we said that error is less than or equal to the next term. So in this case, our next term is the next n value. So if we were at the second degree, okay, then we'd have to go to the third. If we were at the third, we'd have to go to the fourth. And so that's what this is saying. So if we are at that n in general, then I have to go to the next derivative, to the next factorial, and to the next power. Okay, so we're going to have to plug all of that in. But wait, there's more. And we're going to practice this, so don't freak out on me. There's this thing called or Z right here, the z. And so the z is this arbitrary value that we're going to have to go look at. And we want to think about it more in terms, oh, that was a fun color, in terms of that whole thing here. So this right here, this entire thing is kind of like the absolute max because it's in the absolute value bar. So it's the absolute max. So if you get a -2 versus a 1, then 2 is the absolute max, okay, of the f to the n plus 1 derivative here between your c value where you're centered and that x value that you're plugging in. And so that's the hardest part, is figuring out what that right there is. So that's what we're going to practice a little bit before we go and do the whole big kick kaboom. Okay. Okay, so let's do that. So here, let's say that the next derivative was just e to the x, like maybe the function was e to the x. So this is my next derivative. And so I'm going to go ahead and graph this e to the x. And they said that we were centered at 0. So we were centered at 0. And then they gave me an x value of 1. Okay? So the only place that I am looking for the absolute max is between where we are centered and what we are plugging in for the x value. All of this is already positive, so the absolute max would occur right here. And so that happens when x is 1. Remember, this was the graph of e to the x. So what is the absolute max? That f prime of n plus 1 of z is equal to e to the first. Well, if we knew like all of the e's and everything, then we just might as well have started with that. So e, remember, is this irrational number. It's not very fun to work with. We'd still have to approximate it. So if your e is like 2.7, la 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 la, and so I'm just going to say that this is less than or equal to the next value that's kind of closest to that, which is 3. And so that's where I will probably use, unless I have a calculator to actually use E. If I don't have a calculator, I'm going to go up and make my error a little bit bigger. Okay, but you can never make your error smaller. You can make it bigger. Okay, so here again is my next derivative, is that e to the x. And now they're saying that I am centered at 0. And the x value, though, is over here at -0.1. So now I'm looking right here. So where is, and it's all positive, so I don't have to worry about the absolute value bars yet, but now the absolute max happens at 0. So that happens at e to the 0, which is 1. So I don't have to do any more rounding or anything. 1 is a really nice number to work with. Okay, let's go see this -e to the x. So I want to look at the absolute value of that. So the absolute value of this -e to the x is going to be just flipping it over and getting e to the x. So I want the absolute value of that. So in this case, I will be using e to the x. And over here, if I hadn't seen that and I was looking between, here, let me just write it out again. Here, eraser. This is the -e to the x. This is the absolute value of -e to the x. Okay, so here if I was looking and it says I want to look where I'm centered at 0, and then I am plugging in an x value of 1. Okay, so once I have that, then if I'm now highlighting between 0 and 1, if I hadn't have done the absolute value yet, okay, is over on the left. Well, I'm looking for the absolute value max. So even this value at 0, absolutely, this is farther away from that x-axis. So I would want to say, well, that's like this negative e to the first, okay? But here, once I take the absolute value of it, again, I would see that that would be, the absolute value would just be e to the first. And over here, when I see this absolute value, then I know that that is e to the first. So the absolute value of the next derivative of z is that e to the first. And again, we're going to approximate a lot of times and use 3. Unless we can have our calculators, then we can still use e. Okay, so let's look at this one. Oh, and up here, I much prefer to just kind of always look at the absolute value graph. I think it's way easier. Okay, I wouldn't have ever have used that one. Okay, so let's look at cosine. Cosine looks like that, kind of, and we want to take the absolute value of it. So I'm going to take the absolute value of cosine when I'm doing this. Pretend that those are all equal, okay? So this is at what, pi over 2, it's my 0, negative pi over 2, okay? And so when I look at those, um, I need to fix that on my key. I was just looking. Okay, so when I look at these guys, I am approximating now. It said that I'm going to be centered at 1/2 on here. Oh, fun. So 1/2, let's see, pi over 2 is bigger than 1, and 1/2 is smaller. So I'm centered at 1/2, and then I am looking at 1, which again, pi is like that 3.14 over 2, so that's greater than 1 over here, okay? So I am looking between these two values. So here, oh, go away. I don't want you group 1. So here, I can see that the absolute max is happening at 1/2. So this f of the n plus 1 now of z is cosine of 1/2. And if I could perform cosine of 1/2, I wouldn't need these polynomials to begin with. So I'm like, I'm going to over approximate what that is. And what's nice is that the biggest that this could ever be on a cosine function is 1, right? Because it was between -1 and 1, and then we took the absolute value. So now it's between 0 and 1. So this has to be less than or equal to 1. And you guys, whenever this is free response and I don't have a calculator, then I'm always, for sines and cosines, I'm like always going to 1, okay? Because that's like the absolute max and I'm making it a bigger error. I can't make it a smaller error. So I just go to that biggest error and go from there. But if I had a calculator, I wouldn't do that. I would stay with the cosine of 1/2 when I'm plugging everything in. Okay, so next, we are going to actually put this all together. So here's the third Maclaurin, and we used it to approximate sine. So I said the original function, the absolute value here of that original function minus the third degree. See how it went to the third and the third? Okay. Of this is less than or equal to, and if I went to the third degree, the next one I'm going to do here for my error is the fourth degree. So I want the fourth degree of z times my x minus where I'm centered to the fourth degree over the 4 factorial. So if I had started with sine, I want to get to the fourth degree. So sine goes to cosine, goes to negative sine, goes to negative cosine, and goes back to sine. So the fourth derivative of sine is sine. And if you remember, sines and cosines, they kind of end in their derivatives and they go back to the original by the fourth, okay? So I'm looking at this sine. So I'm going to look at the absolute value of sine. Sine of 0, sine pi, and that's as far as I really need to go out. We said we centered it. We centered it around 0. And we're going out to 0.1, which is definitely less than pi. So I'm looking right here. And I know I went out too far, but that's okay. It's hard to get it really close. So as I see that, I know that this has to be right here less than or equal to the sine of 0.1. Okay, and this is what I was kind of saying, and then I'm going to go ahead and simplify this. If I could do that, then why do I need this to approximate sine of 0.1, right? Okay, so we're going to say, we're going to go ahead and go bigger on that so we can actually get an approximation without having to use our calculators. If we could use our calculators, we would plug all of that in, but then it's like, well, why if I just can use my calculator and plug that in? Okay, so we're going to say, that that sine, I know the biggest I could ever get out is a 1. So I'm going to use a 1 and put that to the fourth over 4. And if you wanted to work all of this out, let's see, let's do it together. So that'd be 10 to the fourth down there. And then 4 factorial, 4 times 3 times 2 times 1, right? 4 is 12, 24. And then you can make that really small. 24 with 1, 2, 10, 4. Okay, so yeah, it's a really, really small error. Sorry, I'm running into myself here. But it's going to be really super small. Sorry, you guys, I'm still trying to get used to all of these little gadgets. But it's going to be really, really small here. And if I went and put that into my calculator, oh, what did I do? Come here. I'm sorry. Hold on, pause. There, now I can get it up. If I went and put that into my calculator, I'm going to see that sine of 0.1 is 0.099. Let's see, I did it 8, 3, 3, 4, 1, 6. Okay, and it keeps going. And so if I looked and plugged this in up above and looked at the difference, here I don't think I did it, did I? So let's go plug that in to the third degree as well. Okay, so we're going to plug in 0.1 minus 0.1 to the third divided by 3 factorial. And I got it to be 0.099833 repeating. And so when you see the difference of those, so minus the sine of 0.1, you're going to see that that difference is negative 0.0000. Well, here, my calculator said negative 8.33 times 10 to the negative 8. So it's really super small error that you have. So just by going to the third degree Taylor polynomial, you've got an amazing approximation for sine, even though we even rounded up from that sine of 0.1 here. Okay, we rounded up from that sine of 0.1 to be the 1. We still are saying, hey, we've got a really good approximation. So that's something that's super cool. All right, do this really quick. Times 4, 3 times 2. Yeah, so this one was 4.16 times 10 to the negative 6. And in fact, yeah, we were even better than that. Okay? So to me, this is amazing. Like you just got a polynomial and you could approximate what sine of 0.1 is by plugging it into this. This is something you can easily do by hand, and you can approximate sine of 0.1. I mean, it's so cool, you guys, what you can do. All right, let's go to the next one. So here it says f is a function, has derivatives, da, da, da. So here we're going to the third degree, about 0. And here is what it says for all n between 1 and 4. This is what that derivative is. So if I'm kind of looking at it, if I said, well, the first derivative would be 1 over 2, because I'm just plugging in 1 and 1. The second derivative would be 2 over 3. The third derivative would be 3 over 4. And the fourth derivative would be 4 over 5. Okay, so I see that. And it says, of the following, which is the smallest value for k for which the Lagrange error bound guarantees this guy? All right, so I was centered at 0, and my x value I'm plugging in is a 1, and I went to the third. So let's go see if we can set up. There's the actual minus the approximate, has to be less than or equal to the next derivative. Oops, that's too big. Not a, here, it's a fourth, not a third. Okay, third to fourth. The next derivative's max value times my x minus my center to the fourth over 4 factorial. We said this guy was a 4/5. 1 to the fourth is 1 over 4 factorial. So what is that largest value? So let's see, that's 4 over 5 times 4 factorial. So that's 1 over 5 times 3. I don't know, how much do we have to simplify it? Oh no, we wanted to leave it here. Okay, so 4 over 5 times 4 factorial is B. Excuse me. So I'm going to pause. That's going to just be kind of part 1 of that. And then we will finish this next section for the part 2. Kind of give yourself a little break on these notes.